are from Group 1 and we will be presenting about our seismic interpretation project on Bundi Field. I'm Arfa and I'll be taking you through the introduction, project outcomes, and project workflow. Seismic interpretation is known as the extraction of subsurface geologic information from collected seismic data. And the interpretation can be done qualitatively depending on the interpreter's geological understanding to make valid interpretations, or quantitatively based on physical variations of amplitudes, phases, and frequencies that are used to predict hydrocarbon accumulation. Bundi Field is located in the northern part of Malay Basin, and this project has taken data from two wells which are from Bundi 1 and South Bundi. These wells are located 280 km north-northeast and 275 km north-northeast approximately from Kemaman supply base respectively. Bundi and South Bundi wells are both wildcat wells that are drilled by ESO in block PM5 to test the hydrocarbon and reservoir quality in that area. So early exploration activities that were done during the pre-1980s in Bundi Field discovered that these wells are both gas fields based on the well data. So our project outcomes is to study the Bundi Field's geologic structural subsurface based on well data from Bundi 1 and South Bundi. Not only that, is also to generate subsurface and seismic well tie of Bundi 1 and South Bundi by correlating its seismic data and well data. Last but not least, it is to be able to understand and do picking of faults and its interpretations. So our project workflow is to first of all import the data into Petra software. Then we did seismic well tie and well correlation. After that, we did horizon picking and fault picking. Then we generated surface maps and did time to depth conversion. And we did its interpretation and then comes to a conclusion.
Hi, my name is Kartaina. So now I'll present to you about methodology and surface map. So for methodology, firstly, import seismic data and realization. Realization is to make a physical representation of a virtual volume, or for making a physical representation optimized for specific usage. 3D Bundi seismic data consists of 815 inline from 290 ms to 1105 ms and 3401 crossline, which from 603 ms to 4004 milliseconds. Secondly, import well data and well log. It consists of many kinds of logs such as gamma ray, neutron density, and etc. Sonic log is used to evaluate petrophysical properties in the wells. Next, sonic calibration and synthetic interpretation. The stratigraphy of the Bundi 1 well can be correlated with sub-Bundi well via well correlation method. Seismic well tie is done to bridge the gap between time and depth domains by doing synthetic seismograph. Furthermore, 2D interpretation, horizon, and fault picking. First step in seismic interpretation is fault picking. Marking faults ensure a clearer view of horizon displacements in the seismic data. Horizon picking is done based on well log data that were interpreted during well log correlation. Moreover, creating time surface map. Time maps are produced from the interpreted horizons and its unit is TWT. Producing this map is done simultaneously with quality controls of seismic interpretation to avoid misties. Next, creating depth surface map. Time to depth conversion is done to its interpretation. Last but not least, creating time slice map to evaluate correlate channels formed in the subsurface with surface map. So now, let's proceed to the result and discussion. So this is a surface map in TWT. As you can see here, it's elevation time in milliseconds. The map shown above is a surface map, which is a two-way time map. In order to obtain or design the TWT map, we should first conduct the horizon and fault interpretation. Surface map velocity is important in order to understand a better structural uncertainty. As you can see from the map above, the TWT is increasing from west towards the east. The shortest time for the map is negative 1300 milliseconds, which is represented in red color, while the longest time shown above is negative 1750 milliseconds, that is represented in the purple color. A shorter TWT signifies that the datum is at low elevation and vice versa. The 5 grey lines in the map are faults that are successfully detected. 3 of the faults are located at the northeast, which is here, here, and here, while one of the faults is detected at the southwest, here. So now for the surface map, which is depth. As you can see here, it is elevation depth. The map shows above is a surface map with depth. The depth map is obtained after the depth conversion has been done on the surface map. The highest elevation for the map above is negative 1,320 meter, which is shown in red, while the lowest elevation is negative 1,920 meter, that is represented in purple. We can see the elevation same where it is increasing from west towards the east. There are also 5 faults detected. 3 of the faults located at the northeast, while 1 of the faults is detected at the southwest. That's all from me, thank you. Now I'll pass the floor to Albert.
Assalamualaikum and very good day. My name is Muhammad Daniel and I'm continuing with the structural interpretation of the Budi wells. So the first interpretation I will be is basically regarding the fault interpretation. So as you can see in the figure in the lower right corner, this is the seismic section in line for episode 488. So in the section below, you can see that there are actually 2 faults in the range of 1,200 meters to 2,500 meters. So faults are the discontinuities of layers and the fracture zone between 2 blocks. The faults are identified by the displacement of the sequence boundary. The middle part of the fault is the hanging wall that has been dropped down due to rock mass movement. In the upper left corner is the 3D fault surface. So the highest elevation for the fault surface is negative 1,500 meters, while the lowest elevation is negative 2,500 meters. So the fault is picked with the interval of 100, and the chosen interval is followed by structural field. The small interval would give a higher resolution of the surface, but for this fault surface, the interval that we had used was quite high. So in the image in the upper left corner is the fault in 2D time, and in the lower left corner is the surface map in 2D time with gray markings that are representing the faults. The upper right image is the fault pickings in depth. So from our observation, we conclude that fault 1 has a dipping angle of 60.43 degrees, dipping azimuth of 359.94 degrees. Fault 2 has a dipping angle of 47.14 degrees, a dipping azimuth of 90.39 degrees. Fault 3 has a dip angle of 52.33 degrees, and dipping azimuth of 130.02 degrees. And fault 4 has a 69.02 degrees dipping angle and 351.03 degrees azimuth. Fault 5 has a dipping angle of 72.89 degrees and a dipping azimuth of 354.43 degrees. From the seismic section, we have also discovered a few structures such as an anticline and syncline. So in the blue circle, you can see that there's a U-shaped structure which is indicating of a syncline, and in the orange circle, you can see that there's the strata is continuous upwards, which is an anticline. We assume that the decline is caused by the intrusion of the igneous rock from the basement of the Malay Basin. Next are the channels. Viewing the time slice at z equals to -54, we found channels. So which is represented by the green circle and the yellow circle. So both structures in the circles are actually channels. The manual shape of the channel can be seen clearly in the C shape or the horseshoe shape. The yellow circle is the manual channel with high seismicity, and the light blue circle is the street channel. So on the right side of the slides, actually is the channels, but viewed from X line equals to 2,109. Now I will allow for Kura to continue with the seismic stratigraphy. Thank you.
Hi, my name is Vicky Zijan and I will present the seismic stratigraphy. Okay, now I will present the sequence stratigraphy at inline 488. So from this seismic section, we can see a total of 6 sequence stratigraphy, and we can differentiate the sequence stratigraphy by looking at the changes of amplitude and frequency. So for the first sequence stratigraphy, what we can see here, it has high frequency with high amplitude, where we can see the amplitude here is very high and it is very distinguishable. We can see it with our eyes clearly, while at the second sequence stratigraphy, it has a medium amplitude with medium frequency. We can see the lines here are more fatter than the first sequence stratigraphy, and the distance between the lines or the layers are a bit far from each other, while at the third sequence stratigraphy, we can see here it has high to medium amplitude with medium frequency. While at the fourth sequence stratigraphy, we can see here in this section, it has medium amplitude with low frequency, where we can see the lines are more far from each other. At the fifth sequence stratigraphy, we can see here it has low amplitude with low frequency. And for the last one, for the sixth sequence stratigraphy, we can see this section has medium amplitude with medium frequency. Okay, now I will present the terminations at inline 105S. So from this seismic section, we can see a total of 5 onlaps, 5 sets of onlap. And onlap usually occurs in the periods of transgression. So it terminates against an initially inclined surface. Let me draw. Okay, so this is the initially inclined surface, this one. And then the layer here, in yellow, the layer here terminates against this initially inclined surface. So this is what we call onlap. So from this seismic section, we can see the direction of the termination is in west to east direction. Okay, lastly, for conclusion, the data used in this project are taken from Bundi 1 and South Bundi, and we found out that the trial is very useful in order to make fault modeling and also in seismic interpretation. Next, horizon and fault interpretation are very important in order to obtain surface map with depth and surface map with velocity. And we use a total of increment of 50 for horizon picking, and we use increment of 10 for fault picking. This is for us to get a clearer image of the surface map and fault surface. And last but not least, it is also proven that the surface map with depth gives a greater resolution than the surface map with TWT or two-way time. Okay, that's all from our group. Thank you.